thing I love most about robotics is the challenge of figuring out what makes things function intelligently in the world. Sensing and control, mechanical design. How do we control the robot fingers so that they're able to achieve some of the dexterity that people can achieve? And robotics at Harvard has had a wonderfully experimental flavor. We build things and test them and make them work in the real world. It's not just a theoretical exercise.
Soft robotics is an emerging field within robotics. In this lab, we essentially say that there's a huge opportunity to apply small to moderate levels of assistance to people. You don't need to give them superhuman strength, but that in itself can have a pretty big impact in terms of their mobility and quality of life. This could be people who've suffered a stroke, it could be elderly people, children with cerebral palsy. So we're trying to think about how do we develop new types of wearable technologies that allow them to move around more naturally like a healthy person.
What we're trying to do is make robots smaller, softer, safer to interact with, more effective because of they're either more agile or can maneuver in places that big bulky robots wouldn't be able to do. Example applications include search and rescue, hazardous environment exploration, biomedical applications, things inside the body, things where you wouldn't want to put a human or an animal.
One of the applications that I'm really interested in is whether you can get robots to construct things for us. Ultimately, what would be really cool is if you had a disaster area or there's a flood, and instead of sending a bunch of people into a dangerous area, you sent a bunch of robots and they picked up the sandbags and they made walls and levees. You can't make a robot unless you understand mechanical engineering, electrical engineering, computer science, and then it actually helps to understand biology because biology is the best examples of autonomous systems. I do try to work closely with people from many disciplines. In fact, that's what I like a lot about being at Harvard, is that that's so easy to do.
It's a great place to find academic collaborators and certainly medical collaborators as well.
Key benefit of SEAS is that although we're growing, we're still somewhat small. That makes us very nimble, very agile. I mean, we can put together interdisciplinary teams very quickly.
We've really reached an important cusp in robotics. There'll be any number of important applications in industry, households, hospitals, factory floors, all sorts of new places.
Almost every application will have multiple robots together.
Assisting with tasks that are difficult, dangerous, extraterrestrial, whatever they are.
The number of robotic startups taking the ideas from research, turning them into practical applications is skyrocketing, and we're very excited to be part of that.
If you think about the last 20 years, the internet has really transformed our lives and the way society works. But going forward, I think robotics is going to be playing that big a role.
Robotics is one of the most successful and attractive concerns for the technology company like WeCare IT Solution. According to the Chief Training Officer,
is an interdisciplinary branch of engineering and science that includes mechanical engineering, electrical engineering, computer science, and others. Robots deals with the design, construction, operation, and use of robots, as well as computer systems for their control, sensory feedback, and information processing.
For humanoid robots, or legged robots in general, keeping balance is critical to being able to carry out any task. We've decided to tackle this head-on by feeding the balance sensations of the robot back to the human as forces on his waist. That way we can take advantage of the natural reflexes and the learning capability of the human to be able to keep the robot balanced.
So we try to give the human as much freedom as possible. So the suit is a full body suit, so the human can move all the arms and both legs. And the idea is that the robot is going to follow exactly the same way. The human also has handle controllers where it can push a couple of buttons, and those buttons are responsible for controlling the hands of the robot. So if, for grasping or releasing, so we control the force that which the robot is grasping its object, very firmly or very loosely, or even to let it go.
We also have a camera in the robot's head, where your head would be, and that vision that the robot sees is fed back to the operator in some vision goggles. When the human wants to do more delicate tasks, things that really require vision and strict positioning, he can use the goggles and do more precise manipulation with his hands.
So currently we have the whole actions taken by the robot is commanded by the human. but we know that that may be not the ultimate solution for the problem. So we want to implement some
Much of the robotics research focuses on the specific industrial tasks, but on investigations into new types of robots, alternative ways to think about or design robots, and new ways to manufacture them. Other investigations, such as MIT's Cyberflora project, are almost wholly academic.
An important transformation and it happens all the time.
People try to bring all the tools and stuff that they learned in class into this particular project, and that is an exciting process.
It's definitely my favorite class right now. We're working on making a goalie robot that can quickly maneuver the arm around in order to stop a ball.
Our whole goal is being able to track a soccer ball as it comes into the robot and then actually be able to repeatedly kick it.
And these are all challenging problems to look at. There's the kinematics, the dynamics, the vision, and all of this computation that it has to be done in real time. So it's great, yeah.
So what do we do about the top corner or the bottom corner? Because then we've got to bring this all the way out.
It's a good combination of brainstorming and throwing out ideas and doing the calculations.
We have a controls team, which is basically in charge of saying, is this feasible using the sensors and information that we have? We have a manufacturing team, which will be in charge of making it.
Another member of my team is focusing on computer vision, so taking input from the different cameras and then using that to try and figure out the trajectory of the ball.
You don't know how much control and how much processing it takes to just move your leg until you try to build a robotic leg.
Doesn't it give us enough mass to get the momentum we want?
And you don't know how much it takes for your mind to just move your arm in 3D space until you have to build an arm to block a ball.
We're just getting started, so let's see how it goes.
I'd be dishonest if I didn't say it's a little panicky right now. It's a very aggressive timeline.
We have to put our heads down a little bit here and do a grind for a couple of days and make sure we have something at the end of the day that actually works on competition night.
The harder we want to kick, the more likely our robot leg is to break.
Everyone's feeling the pressure, the time crunch in order to get this thing to work, but also everyone's very motivated to do it.
Even though we might all be able to get our individual pieces together, it's being able to do that in real time with a real soccer ball.
I think we can kick the ball, I think we can see the ball, react to the ball.
I do think we'll be able to do it. I think we can do it.
I think MIT especially is one of those places that says, oh, you want to learn something? I'm going to throw you in the deep end and make you fail a little bit, but you're definitely going to come out of it a better engineer.
At the end of the day, robotics is one of the coolest things any mechanical engineer can learn.